Still awake? Okay, good. So let's get started then. I know that we have a little bit of flexibility with the schedule for today, but I'm gonna try to stick to my time, not trespass to other people's a lot there. The people who know me know that I'm not very good at being brief, so, but I'm gonna try my best, okay? Today, we're going to discuss a little bit about the use of foundation models for geospatial data, right? And there is quite a bit of background that's actually need in order for you to be able to fully follow what we're going to discuss here now. I'm going to try to give a little bit of context, but like it's very hard to bridge that. But I do encourage you, if you want to better understand this discussion that we're going to have today, like because this is going to be recorded so you can rewatch later, for you to access the material that we have recorded and posted on the Spatial Ecology website. So these two QR codes that you have there, you're going to have all the material for 2023, which is already available online. In 2024, Giuseppe is going to upload soon, perhaps next week or so. Okay? Very well. So what's the agenda for today, right? So like very quick intro, right? Just trying to bring everyone to speed. Before we dive into like foundation models, I want to introduce what are these building blocks of foundation models. So we're going to discuss a little bit about transformers, right? For the ones that are not familiarized with that. By the way, show of hands, please. Who knows what transformers are? I see many hands doing these, like, kind of, okay. All right, it's okay, it's okay, yeah. But who has familiarity with neuronal networks? There you go. Okay, now we are talking. So, all right. So now I know that I have to introduce transformers, which is okay. And who has used a foundation model before? Absolutely no hands. Okay, great. So that's the goal for today, okay? Everything else is basically just trying to give enough context and background, all right? So the foundation model that I picked specifically to discuss with you guys today, so like there are many foundation models for all the types of applications, is gonna be this one, which I call Prithvi, but I pretty sure I'm messing up with the pronunciation. So if there is anyone who knows how to pronounce this word properly, please step in. And this is a model that was developed as this collaboration between IBM and NASA. So like we're going to spend all the tutorial parts discussing that. The tutorial is going to be like as usual, this hands-on practice, right? So like we're going to step into the code. And the idea is that by the end of the tutorial, you guys are going to play with your own data set using this model. So like stay tuned for that. I think it's going to be a lot of fun if it works. So like there is that still. Before we get started, let me introduce myself properly, right? So, like, I have a PhD in neuroscience, which I know raised a lot of eyebrows when I said that, right? My work is mostly as a machine learning scientist, so I develop machine learning models, right? Uh, Most of it has been towards like developing foundation models for like biomedical data sets. So like my work is like with brain recordings, trying to leverage knowledge from like single cell single cell data in terms of like gene expression and how they might be associated to disease, right? And how ultimately we can design drugs that can cure those diseases. But if you focus, you guys can see the mouse, right? Okay, great. If you focus on this little matrix here and this other one, right? Essentially, when you get to this point, doesn't matter what's the data that you're using. All the data engineering, of course, is basically what you guys are the expert at, right? Once we pass that barrier, we have the data in a table format or a matrix format, then we are all talking the same language, right? So like, and that's why I can contribute a little bit to the formation of your knowledge overall, all right? Very well. So the people who have been following the course, right? We have discussed in excruciating details, right? How we build neuronal networks, most specifically for like supervised learning problems, right? So that's being when you have a ton of data with like several features associated to these data points, and you'd like to use this data to make a prediction about something, right? Being data classification, being data regression, or whatever, right? But on the other hand, right, so like what we are seeing on this far right side, right, is what essentially are some of the examples of foundation models, right? So like when you're talking about foundation models nowadays, the first model that comes to mind is ChatGPT. Who here is using ChatGPT almost on a daily basis? Come on, be honest. Okay, right. All right. So like ChatGPT is this conversational agent that's like really powerful, right? You can ask questions to it. Basically, it's like a proxy for what you're doing by yourself on Google before, right? And then we have this other model called DALL-E, also from OpenAI, right? Which you can use a prompt to generate an image, both based on this idea of transformers, right? Now, there is quite a gap between these two, as you can imagine, right? So because I have covered in details the construction of neuronal nets, right? So like everything about the architecture, what's the rationale between like adding nodes or like neurons to a layer, increasing the number of layers, how the whole training process takes place. I'm not going to cover that. So we're going to keep it very high level, right? I'm not really getting to the specifics of that. But I am going to try to bridge this gap a little bit with this little background review that we're going to do in the coming slides. Okay. Any questions about the roadmap so far? Everyone on board with this plan? Great. Right. So a little bit of like this knowledge that we're going to try to bridge here, right? So like there is this very useful comparison, right? That's Lian LeCun, the winner of the Turing Award in 2022, he made in the past, which like most people, they do work with like supervised learning frameworks, right? As we just described. And from my very superficial knowledge of this geospatial domain, most of the applications do fall in this supervised learning framework, right? But in reality, the bulk of the data that you have, bulk of the problems, they might be considered as unsupervised learning. You just have a ton of data and you're trying to leverage or extract some useful information from this data, right? And then, of course, there is reinforcement learning, which like he makes the comparison to being just like the cherry on the cake, very task specific, which hardly we find an application for geospatial, unfortunately. So like every year I try to come up with like analogy of what would be an application of reinforcement learning for geospatial domain, and nothing other than navigation comes to mind. Okay. So let's just cover some of these unsupervised learning techniques that I'm pretty sure you guys have heard of, right? So for example, one of the classic unsupervised learning technique here is clustering, right? So like, who has used k-means before? Everyone has used k-means. So like hierarchical clustering, like spectral clustering are other types of clustering techniques that are not as popular, right? But the overall goal is always the same, which is to try to group data points, right? By the degree of similarity that they have in terms of like what's the commonality at the future space between these data points, right? And then we have dimensionality reduction, right? So like when you're trying to condensate or like compress the information that you have in many features, when you believe that not all the features, they are being as meaningful towards like the amount of information that they carry, right? So like you'd like to visualize that data in a 2D or 3D space for like the sake of comprehension. So techniques that people usually use for that are PCA, which is like linear dimensionality reduction. Who has used PCA before? Great. UMAP. Who has used UMAP before? Many hands. Variation autoencoder. Okay, I see 2 hands there. Great. So like we have material on autoencoders in our classes. So like if you'd like to learn more about that, please feel free to access the content of our recorded classes. Okay. And now finally, we have sequence learning, right? Although sequence, it's very poorly defined in this case, right? Because these methods, they don't necessarily just work with the idea that you have serial data, right? And in fact, these type of approaches have been used extensively to just learn features from sets. So like the difference between series, right, is that you have actual order to the data, right? So like you have a specific organization to your data, that being space or time, right? And then you have sets where it's just like there is no order specified to those samples. They just to some extent belong together, right? As being part of a set. And for this type of problems, right, we have the traditional machine learning, if you will. In traditional, I'd call like these recurrent neuronal networks, for example, that the people who work with time series, I'm sure, have heard of, right? So it's essentially using neuronal networks to predict future time points based on some context that's being provided as like the past time points. So like how the data is, how the features are changing over time for that specific observation, right? Then we have the improvement of recurrent neuronal networks, which are LSTMs. Then in 2017, things changed dramatically, right? Which was the Transformer paper when it came out, okay? Essentially what they proved there is that this way of learning time series and sets in a sequential manner, first, it's very slow because it's sequential, as you guys can imagine. So right, there is very little room for parallelization there, and prevents the model from accounting or learning from long distance relationships, right? Because it's sequential, most of the information that's carried is actually things that are close to the point that you're trying to predict. So things that happen really far in the past, they tend to matter less for a model that's being trained in a sequential manner, right? And transformers are very good at handling this type of problems, as we're going to see in a little bit. Most of the applications with transformers are based on the idea of learning language, right? So like you guys have heard of like large language models, I'm pretty sure. ChatGPT is one of them. There are many others that came before. BERT perhaps is the most popular one, and you're gonna see why, like why this framework is so powerful. And then there is Llama, there is Lava, there is the infinite models nowadays, right? Everyone has its own large language model at this point. So I think the idea now is like, since the transformers is such like a crucial building block, right? Let's try to understand a little bit more about this model, right? And how we can leverage its capabilities to our specific problems, right? So what differentiates transformer in the first place from previous neuronal networks, right? So there is this one thing that I just mentioned about making these predictions, accounting for more than just like the previous time points, like that are very close in time, right? So you're capable of learning things that are far in the past, which is one of the attributes that people believe that makes transformers so much better than recurrent neuronal networks, right? It's very parallelizable, right? So like it's very GPU friendly, and like when you're talking about high performance computing, this is a property that we want our models to have, right? And they're very versatile. So like although most of the applications they have been done for like the language domain, like now we have transformers for like learning from image, transformers to learn from like sets. I'm using transformers to design new drugs, as I just introduced in the beginning, right? So like I'm using transformers to learn how I can detect like specific receptors in cells and design a drug that's gonna bind to it more effectively. So like the possibilities for transformers are really infinite at this point, okay? But how are they implemented, right? So let's talk about like in this very overview, like this bird eyes view of what the transformer is trying to implement. The original transformer had an encoder and a decoder block. So like that's very similar to other architectures that we have seen in the past, such as the autoencoder. So you take an input, which in this case is text, you encode this input to a latent representation, right? Are you guys comfortable with the idea of latent representation? Anyone here doesn't know what latent representation means? Okay, so like you're gonna encode, for example, single tokens of these input series that you're giving as input, right? You're going to encode that to, for example, a dictionary index or so. You're going to find now a vector representation of that original word. So like all the operations are going to be done at the vector space. So that's essentially the idea of finding a latent representation that might be encoding the original data on its domain, right? So in this process of compressing this information to this latent representation and decompressing, you can train these models for all the sorts of things. That being next word prediction, for example, auto-completion. You know that like when you're typing a word, your Google keyboard tries to suggest what most likely you're going to say next. So like that's one of the applications for that, or even translation in language, right? More specifically, when you're talking about these transformers, they have series of like this encoder and decoder blocks, right? So now let's see what these blocks they stand for, right? So I just told you that the starting point for these models is essentially finding this latent representation. So how you extract this latent representation, in this case, represented by X1 for the word thinking and X2 for the word machines, right? The process of finding this latent representation is very task specific. So for example, you could use this one-hot encoding approach. Who here knows what one-hot encoding approach is? Okay, few people. So like in the case of a dictionary, right? Again, if I say, okay, I'm going to have binary code, right, for all the words that are part of my dictionary, right? So like when I say Earth, right, that's going to be code 0001. When I say observation, it's going to be 0010, you know? So like that would be like the equivalent of one hot encoding, if you will. And then the size of this vector is going to be as big as the number of words that you have in your dictionary. Is that okay? So that would be the equivalent of one hot encoding there. Then from this one hot encoding, you find a way to embed this one hot encode to a latent representation that's going to give you this vector representation for the tokens that you're going to be working with. Okay? Am I going too fast? Is this sort of clear so far? It's not clear. Okay, all right. Okay, so this is just the process of like getting your input data, right, to be embedded in a useful space, a vector representation that can be used to learn something from it, right? So like that's the starting point for any model is to have like a vector. If you guys think of like the other models that you have used, random forest, for example, you have observation by features, isn't that right? Right? What we don't usually do is to try to change the representation of this data, right? So like most often when you're doing random forest, you don't try to go from 40 features to 30 before you even start, right? Could you do that? You could, but like that's not a thing that people in random forest do, right? But when you're talking about using something like transformers, this might be useful. Why? Because you remove part of this original dimensionality of the data that's not useful, right? So like you learn a condensed representation, right? Removing all these things that they don't matter, that are just noise or that are not predictive of like your task in general, and just work with that latent or condensed representation, okay? So now we have the self-attention, which is, yes.
So this condensation of information, right, is getting the embedding, and you said there's different methods to do this, right?
Yeah.
And then the choice of that depends on your task, right? So a classic one would be the next word prediction, and then the embeddings you get kind of represent the words in some kind of vector space where when they're closer together, they're more similar. Is that the idea?
Exactly, yeah. So like these embeddings, they might be trained for all the sorts of purpose, right? So for example, you might want the embedding to put together words that they have similar semantics. So like all the words that they're trying to convey in the same meaning to be encoded in the same space. So when you're trying to retrieve the next word, you don't go all over the embedding looking for the what should be the next word, but you focus on a specific region of the embedding. So like here it has several candidates that try to express the same feeling, if you will, right? So that's the idea of like embeddings in general, but they might be encoding other types of properties. So like it's very task specific, as we just said. Okay. So now, any other questions on this before I move on? Okay, yeah, please.
So does it only work for text, or images also make sense?
Works for any type of data, and that's what we're going to see in a little bit. So like how you embed these things. You can do this embedding using like a fixed encoder. So for example, you could learn this embedding using PCA if you want, right? And use like a linear dimensionality reduction as your embedding technique. Or you can use neural networks. So train this embedder jointly with your model, which is like what I personally do, okay? Any other questions? I'm really sorry if I'm moving too fast. I'm just trying to get to what's the cool part of this, which is like the tutorial. Okay, all right. So the next part is the self-attention part, right? The self-attention is essentially this was the biggest side of this transformers approach, right? Which is that I should be trying to combine the knowledge or the information that's coming from the different tokens when I'm trying to do anything downstream of my application, right? So what the self-attention attempts to do is to try to find the relationship between the tokens that are composing that set or that sequence. In this case of like language, it's a sequence, right? Where like the order of the words are important, because if you scramble the words, right, you might break completely the meaning that you're trying to convey in that sentence, right? So again, the difference between series and sets is the dependence on the order of the elements, okay? All right. So now let's see what the attention is attempting to do, right? So like, let's see first in terms of comprehension, what the attention will try to do for us. So let's imagine that so in this quick sentence here, like I kick the ball, right? As we see on the top, right? I'm trying to understand what kick means, right? So some of the properties that the attention will try to learn would be like, okay, if it's kicked, who kicked? Okay, I kicked, right? So like that's the first information that's being extracted from the neighboring tokens, right? So kicked what? So like what this person did, kicked something, right? Into whom? So I kicked the ball, so like the action was done at the ball, right? So like the self-attention is trying to learn this weighting, right? Between the word that I'm trying to embed or to learn something about, right? With respect to all the other tokens that are part of that sequence. So like when I'm trying to find the representation, right, that I should have for kicked, I'm inheriting information or like aggregate information from all its neighbors, okay? Yes.
Just a slight comment. So please don't apply this today for a football game.
Yeah. So kick the ball, not the person. Okay. So like that's very important. Okay. So now that we have this general understanding of what self-attention is trying to achieve, okay, and if everyone's with me, now we're gonna see how we're gonna use neuronal networks to implement that. So like, is the goal clear to everyone? What Transformers is trying to do and what the self-attention specifically is trying to do here is to try to find the relationship between the elements that compose the series. Okay. If you didn't get anything so far, that's the goal of self-attention. Okay. All right. So how we use neuronal networks to achieve that, okay? So the people who have followed the spatial ecology summer school, they're very familiarized with the idea that every time that you see W's, right, usually you're talking about learning a neuronal network, right? So like those are the weights that are gonna be assigning credits or like assigning the importance of the features that are associated to the data points. And that's exactly what we're doing. So these W's are learned weights, right, that are being implemented via a neuronal network, okay? So now we're gonna find three streams of information, which like are named the keys, and the values, okay? So what these representations are essentially just different projections, right, of the input words. So like these are the embeddings that were extracted using your embedding of preference, right? Now you're gonna find how to project these words to these three different spaces, right? Using these weights that you're training with your neuronal network, okay? And why we do that? The answer is in this slide now. So like in the process of finding, okay, every time that I have a query, right, which the word that I'm gonna give as input or that I'm trying to find its proper representation, right? So like, let's say that we're trying to learn the representation for thinking, right? Thinking has its own embedding that was obtained using your embedding of preference, right? Now, using this WQ, WK, and WV, I have these three vectors, right, that are being used in different steps of the training, okay? The query is always like, what is the information associated to this current word? And the key and the values, right, are coming from like the current word and all the others, right? And why is that? When I'm trying to find how much information I'm extracting from the other words, right, in the series, I'm going to be doing this product between the query associated to the word that I'm trying to learn a representation for, right, with the keys that are coming from all the other words, you see, that are part. So like, that's why I have Q1, K1, Q1, K2, and that you keep doing for as many words as you have in your series, okay? Then after that, right, now we have the output of the network, right, which is gonna go through a nonlinearity, right? The people who did the course with me, they're very familiarized with nonlinearities and activation functions. So in this specific case, the activation function that you're using, because we are trying to find what's the most likely word that we're going to be retrieve from our dictionary, right? Which is very close to a classification task, is the softmax. So you see that at this point, I have a probability distribution almost between how I'm going to combine information from all the other words in my sequence when trying to understand the currents or the current query that I'm giving as input, right? So here now I have a representation Z, right? Which is like the representation that has been learned given the context of all the other words that I have in my series, right? Which is gonna be trained for a specific task down the road. That being like learning a language or like learning how to classify images or classify sets, okay? So these now, it's the new representation after we have aggregated all the information from the neighboring words, which is very similar to what we're doing here, right? So like I'm trying to understand what kicked means. So I'm inheriting all the information that's coming from the neighborhood. Okay? All right, we're very close to the end of this. So like stay with me. If you're lost, things are gonna make sense at some point. Okay? All right. So of course, this what we just did here was for like single words, right? So like you see that I have one vector for thinking, one vector for machines, right? So like that sounds very computing unfriendly, right? So of course, we scale this to be done all in matrices operations, right? Which is why we can very easily parallelize this whole thing using high performance computing later on, okay? So this is just the implementation of what you guys see here, but in matrix shape, all right? Very well. So like, if you guys have picked this idea that we have several encoder blocks, right? As I'm like trying to illustrate here, you probably is wondering when we're gonna be combining all this information, right? If I have like all these blocks. So essentially what we have is that we're gonna have 8 transformers doing this operation simultaneously, right? And in the end of these operations, we're gonna have 8 outputs, right? That's later on, we're just gonna concatenate all together, okay? So we will have, in this case, 8 transformers that are looking at the same sequences, right? And trying to leverage information at the same time, right? So like trying to learn meaningful information about the neighborhoods when trying to understand the meaning of single words or like images, if you will, okay? Is everyone with me? Okay, yeah, all right, like big summary in this slide, okay? So what was the first step, okay? We had a sequence, right? So like in this case was a sentence that was very short, just saying thinking machines, all right? We found an embedding for this sequence, right? Which were represented as these 2 rows by this number of features here. The number of features are dependent on my embedding technique that I picked according to what's the task I'm trying to solve, right? Then we're going to train these neuronal networks, as you guys are seeing here, right? To find meaningful representations for the words that compose the original sequence, okay? We have 8 of those because like we have 8 transformers in these architectures usually. You can have more. So for example, when you're thinking of really large language models, you can have like nowadays 24 of these transformers running simultaneously, right? But each one of them is looking at exactly the same data, right? And trying to find different representations for these words, right? So like they are learning different properties of how these words, they relate to each other, okay? Each one of them is going to give you their insights in terms of what's the level of relationship between these elements that compose the sequences, right? And finally, it's going to give like the summary. So like how they believe that these words, they relate to each other, okay? So that's the overall architecture, all right? So like we have some information about positional encoding, right? That I mentioned to you, which like how do I encode what's the actual order of these elements, which can be done in several different ways. Like they pick a very complicated way of doing that, but no need to worry about it, right? Like what matters for us is that if the order is meaningful to you, you have to make sure that you aggregate that, right? You see that there is positional encoding being added to these embeddings before you even give this as input to the transformers, right? Small detail there. Very well. So like in the end of all this process, right, what we're going to have, it's a map that looks like this, okay? So for another example, let's look at this sequence that says the animal didn't cross the street because it was too tired, right? If I'm trying to understand what's the context or what's the meaning that it's trying to reflect here, right? For us who speak English, right, it's very intuitive to imagine that like it cannot be the street was too tired. When I'm saying tired necessarily, I'm reflecting to the animal, right, that didn't cross the street, right? But for a machine, it needs to be learned from scratch, right? Because like such associations don't exist for a machine. So after the training, a model that has been fully trained, it learns this type of like weighting association, right? So for example, if you pick one of these transformers, right? So for example, the 5th transformer that was being trained here, right? You see that most of the attention is being allocated to the animal. You see it here, right? Very little attention is being allocated to the other elements in the sequence, right? If the model has been properly trained, you can use self-attention to even do some interpretation on what type of relationship between the tokens are being meaningful. And for the people who do like segmentation, right, detection, these type of properties are very useful because you can use self-attention directly to perform segmentation, right? Few things that we're going to be able to explore later. Any questions about this? Is the idea of like what self-attention is attempted to learn here clear? Like the training process might be a bit obscure. I just want you guys to know how this thing, what are the properties that these models are trying to learn. But later on, what we're going to do is to just apply these models. So like, I just want to give a little bit of context on what we're trying to do. Mm-hmm. Right. I think that in the case that we are training with like natural language, right? You never say that the street was too tired, right? So like the type of associations that right. In the data set, right? If the data set's properly curated, which is very important, like for all the people who work very hard in the data engineering, you should like light up a candle and pray for them every day because like that's a very hard task, right? To make sure that the data that you're using to train these models is properly curated and can be used for like the model to learn from it, right? So like you don't have spurious associations such as the street was too tired, right? So like these kind of things are going to be learned directly from data. Okay. You can have a different order, right? So like what matters here is the structure and how the structure of the sentence, right, is conditioning meaning. So like that's what really matters. The order per se, right? We are adding the positional encoding. So like this word comes in these specific sequences, right? In this specific order. So like the idea here is like, how can I leverage this information about how these words, they usually show up next to each other, right? To the context that they're trying to convey here. So like, what's the meaning overall that we're trying to convey? So that's the idea in this type of architectures. Yeah.
And these 8 different transformers that run in parallel, like they're not purpose built, right? They just start off with random weights, and then they all learn just based on these random weights different relationships,
Right.
and then it feels like almost like an ensemble. Like you use a combination of their different.
In fact, yeah. So like, for example, these I just showed to you would be the representation that you learn in one of the 8. So like that would be the 5th attention block there, right? If you look at the attention block 1, right, what you might see is just like a straight line between animal in there, that didn't animal. You see, it would be like a very naive type of association, which is like no more than just learning, okay, these words, they show up in this specific order, right? Sometimes it's like things that are just coming like in different directions and they don't necessarily have a specific meaning to those attention weights, which is like another topic of research in machine learning, right? How to project these learned attention weights to something that can be more interpretable. Because these type of patterns that we're looking at, sometimes they don't emerge spontaneously, right? So like you have to be able to concatenate all this information to another type of representation that could be useful for like interpretation of the model, right? So like explainability is a big deal in machine learning nowadays, right? You want to make sure that like this model works, but why does it work? What did it learn? What type of relationships you're learning here? Okay. Great questions. Any other questions? All right. So like now step even further away, right? So like how these things, they are combined together. So like we saw this encoder as just being one block, but now that we have described what are the elements that compose it, you see that there is a self-attention block there. We have a couple of feed-forward neuronal networks. The people who did the course with me are obliged to know what a feed-forward network is, right? So like that's just like a simple feed neuronal network. You have a couple of extra normalization blocks in there. So you see like this normalized batch normalization going on and some residual connections that turn out to be very useful for training machine learning nowadays. Okay, very well. So now I promise you that like BERT, which is one of these models that were trained for like learning language, would be very relevant for our specific application. And now you're going to see why. Okay, so how do these models train, right? So like one way would be for you to always predict, right, the next word. So like I always go from like having word 1, word 2, and word 3 to predict the word 4, right? Another way of doing that is by randomly removing a word, right? So for example, if I tell to you, the book is on the table, right? So like we have learned this type of relationships because we have been exposed like very often to it, right? But we can shift that. We don't necessarily need to predict always the last word, right? But for example, in a sentence that I'm gonna say, for example, I crossed the blank. Oh, let me write it here. I crossed the to reach the bank. Okay. So like now, what is the word that I'm trying to put here? Any guesses? The street. So you're thinking of a financial institution as bank. Isn't that right? Now, if I say that the bank is a sand bank, what's this word that I'm using there? Right? So like the context is very important when you're trying to understand the meaning of a word. Like we have infinite number of candidates for that gap. But as long as I'm giving enough context to bank, you see that like you can very easily fill up that gap. You see? Okay. So that's the overall idea. So like I'm gonna remove specific words from the sequence and use the context, right? Because for me to be able to perform well in this test, I have to extract as much meaning as possible from the visible words, the one that were not masked. Okay, so that's the overall goal of these models. And that's what BERT attempts to do, to use transformers to learn these relationships. And the loss function in this case is try to minimize your perplexity, or like that would be another type of loss function, which essentially is like how surprised the model is when a word is placed in there, right? So if the model is not surprised at all, that means that this model actually learned something that's very typical from this context that's being provided, right? To the point that, okay, yeah, when you said the book is on there and you said it's stable, I was not surprised. I was really expecting that, you know, like, so that's the type of information that Perplex is trying to encode there. Okay, now how do we apply that for other domains, which is what we actually care about, right? So like who here is doing research in natural language process? I believe none of you, right? I am, but nobody else. So like you can use exactly the same type of approach now for images. And now we're getting closer to like what's really matter for you guys, right? How can you adapt this framework to your task? So for example, if you get patches, is it visible there? Okay, so like this is an image, okay? Like an image, a picture of what could potentially be like a famous spot in Vienna, perhaps, I'm not sure, it's just a castle there. You can break these into segments or patches, right? So for example, this image was broken into 9 patches, okay? Each one of these patches can at this point be considered a token of a sequence. Isn't that right? Right? The difference is that for me to be able to use these tokens, right, I have to still embed them to a relevant representation, which like in the case of embedding words, we're talking about using one hot encode, right? And then from the one hot encode, learn how to project that to a meaningful representation, right? That being PCA or train a neuronal network to do so, right? What these guys at Google decided to do, right, in this vision transformer model, was to turn these images into vectors. So like they just linearize, right? So like for those who are not familiarized, a patch, it's nothing else than a matrix, right? That has 3 layers, at least red, blue, and green in terms of like the information that you have in 3D. You linearize that information by just having like flattening that matrix to be just a single vector. After you have done that, just 1 second. After you have done that, right, you have that embedding representation that is what we're looking for. You can use that or even go from this to even a more condensed representation using PCA or trained neuronal network to do so, right? And at this point, once you have this guy here, right, what was the source of your data doesn't matter. The whole framework can be adapted as long as you reach a vector representation for the elements that compose your sequence or your set. Okay? Is this jump from language to image sort of clear? Like how we are moving away from like finding these vectors from language, right? Using these embedding of words to now embed patches of an image, and how we can leverage the same framework that we have discussed to now learn something meaningful about the image. Lucy, you had a question. Mm-hmm. Right. So I think that's essentially the idea of like using a more clever way of like handling this simple flattening of the image, right? What is a good alternative for the flattening of an image? And you guys, sorry? Right. But we have a neural network that does that as well, which we saw in class. Which one was it, Lucy? Was the convolutional neural network, right? Because it accounts better for like spatial relationships, right? So like you might use that to learn this projection to like this vector flattened representation. You can, yeah, by all means you should, yeah. No need to like reinvent the wheel, yeah. Okay. Any other questions so far? Stick with me. We are very close to the end of this. Like, don't get lost. Okay. All right. So like now we have done this adaptation of the transformer framework to learn from series of patches, right? So like the series of patches now can be used for a downstream task, which in the case of the vision transformer guys from Google, what they wanted to do was to just beat the previous computer vision algorithm that was the winning of this competition called ImageNet, right? So what they cared about is like getting a model to train to classify specific classes of images, right? So like in this case, they didn't really care about much of like the representations that were being learned as long as they are useful for like classifying the images that are part of this data set, right? So if we are training a model to predict specific classes, that's supervised learning, right? So like we're adapting transformers to a supervised learning task. How can we adapt this to unsupervised learning now, right? We can pretty much bring back what the BERT paper did, right? Where they were like masking whole regions of the series, right? Removing words in that specific context. We can do the same thing by removing patches of the image, right? So for example, when I'm training this model, the inputs that I provide to this model is just like few very sparsely sampled patches. Everything else, they're just like placeholders, right? Which are represented by these gray blocks over here. The encoder is exactly the same architecture of the transformer that we discussed before. Okay, so like we're leveraging the same architecture that was used for like learning from language to learn from patches of image now. The tasks that this model needs to achieve now is self-supervised or unsupervised, if you will, because the output is just the original sequence, right? So like we are going from this downsampled version of your image, right, to something that's like it's fully reconstructed now. Can you guys think of any applications perhaps for like the geospatial domain for such a type of framework? Yeah, go ahead.
Like you could try to predict what's under a cloud, right?
That's a great one. So like, for example, these patches, after this model has been trained, right, could be trying to predict what's under a cloud, given the context from the visible areas, right? So like, that's a great one. Anything else? Spread of deforestation, yeah, absolutely. Because you can leverage the same idea of like the patching to also be done in time, because that's essentially what language does as well. So like, absolutely, we can make predictions to the future. And that's a thing that I have done quite a bit of work on as well. Any other applications? I think these two are very good already. So like maybe you can move on. Oh, that's a fly. That's a fly over here. We're bring low. Yeah, we're bring low. All right, so like now that we have discussed transformers, why they're so powerful, right? I think we are finally in the place to talk about what foundation models are, right? I'm going to anticipate already that foundation models are heavily built on these transformers, right? So like everything that we have know as like really intelligent models nowadays, they're built on that. Like some of them, this slide really likes me. Okay, so like GPT-3 built on transformers, right? BERT built on transformers as well, right? And CLIP, which was the first one that was trying to bridge language and images, also built on transformers, as you can see here. But what makes the foundation model really like breakthrough is the scaling laws that they have been observing, right? So essentially, large models, when exposed to like really large data sets, right, they can learn crazy things, right? Which is to get very close to what an intelligent being could potentially be, which is why we see ChatGPT being what it is nowadays, right? So it's not enough to just have a very large model. You need to train these models in really large data sets. So like look at, for example, the amount of data that was used to train GPT-3, which is kind of obsolete now. Even the free version of GPT is 3.5 already, right? These guys, they use 410 billion tokens. So and the way how they give that as like a context is like, by all means, we have trained these models in all the internet. They have seen everything that's publicly available in the internet, and even like some custom data sets that they call books 1 and 2, which nobody knows what these books 1 and 2 are, right? But like most likely, yes, that they just don't want to disclose because otherwise they have to pay for it. But like a lot of data, right? And same with like these image-based ones, right? So like there is now, and that's something that has been happening since GPT-3, right? Is this common crawl. So like essentially they are just like loading things that they find eventually from the internet that don't have necessarily label associated to it, that they incorporate the training process of these models as well, right? So we have talked about the scale. So the scale is very important, right? Second, this whole process is done in an unsupervised manner, right? So like it would be impossible for us to be able to label billions of tokens, right? So like no one can do that. Doesn't matter if you're like using online platform where you pay people to label tokens and it still be unreliable because people just cheat or like they start to just like giving random labels. Yesterday we saw people like on Milutin's platform. Milutin, take care of that, right? Because like the people are just like saying, "Oh, is this classification correct?" Yeah, sure. Like so, people mess up with the labels of your data set, too, right? It's like unsupervised learning. It's very important for that. You don't need labels for anything. And second, after this model has learned some meaningful representation for like data overall, you can start questioning this model for more relevant types of tasks, right? Which is like some of the tasks is what we're gonna see now. And you guys already suggested some of them. For example, removal of clouds, like prediction of urban growth, or like progress of deforestation and so, okay? So that's what foundation model are. Very large models combined with very large data sets that you can very easily adapt for like your own application after they have been pre-trained by a group with a lot of resource, because that's not cheap at all to do from scratch. Okay, any questions so far? How am I doing with time? Okay. Have what? Oh yeah, okay, great. Yeah. Okay, all right. So now we're going to discuss this model, right, with the PRITV. So what is this model and why we are considering this perhaps as this first foundation model for like geospatial data, right? So this model, it's relatively large, although like for foundation models, for example, GPT-4 has billions of models already. So this one has 100 million parameters, which is big, but it's in the lower tier in terms of size of models nowadays. Amount of data that was trained, right? It was 1 terabyte, right, of multispectral satellite imagery from this harmonized Landsat Sentinel-2. Like I know that many of you are working with like Sentinel data, so like hopefully this is gonna be something relevant for your application as well. For those who are not familiarized with this data set, like that's a spatial resolution of about 30 meters, right? With like multiple spectral instruments used to collect this data. So you guys are way more familiarized with this data set than I am. In fact, I just learned about that this week. So like what are the properties of this data set? There is a temporal component to it as well. So apparently images are collected like between 2 and 3 days, which gives also like extra redundancy to the data that's being processed by this model. And in terms of the layers that were used, so apparently the Sentinel, it has up to 12 layers in terms of like what's this spectral composition of the data, right? But to train this PrettyV model specifically, they use visible and infrared mostly data, right? From this data set that was collected. So it's a smaller representation of the overall data set. Now, how was it trained, right? And you're gonna see that this is essentially what we have discussed for like the transformers and later on to mascot autoencoders for the auto-completing tasks, right? So there is the sampling part, right? The extraction of the tiles, which you guys are very familiarized. You're all very experts on doing that, right? Now, once you have done that, what you do is to do the training by using the same type of framework that we have discussed for the mascot autoencoder. So like we're gonna remove some of this information, right? And it is better represented here. So like the removal of this information is done in space and also in the spectral bands. So you see that like I might have that information for the visible range, but I might not have the infrared corresponding to that. So like the way how I drop information for any specific region varies, and that's done randomly, right? After I have done that, the training framework, and you see that they were careful enough to represent this exactly the same way how the mascot autoencoder is represented, is that only the visible patches, so the information that was kept, is sent over to the encoder, right? And from this process on, what this decoder is tasked to do is to try to make inferences about the missing regions. So like these gray patches that we see over here, right? The output then is the reconstruction of this image, right? So like what's the best guess that this model can do, right? Given the information that was given as context. And then finally, the loss function that's used is just trying to compute the mean square error between what's the ground truth information, right? And what's the reconstructed image. Okay? Questions about the framework that we're using here. If you understood the mascot autoencoder, that's exactly what the mascot autoencoder was doing. If you didn't understand that, but you understand this one, they are doing exactly the same. Yes, please.
I guess that for each band, there should be at least one, let's say, visible patch.
You can drop the whole
All of
band,
them.
like across the whole band, and use the other visible patches, like both in space and across the bands to try to.
No, but I mean, to be a valid training sample or training patch, there should be at least, or they're not related in terms of. I was just wondering if, I mean, because there we see the image and the stack are the bands of the image, and therefore, if we mask for one single patch, if we mask all of them, then we discard it, okay? But then if we keep only one, yeah, I was just trying to understand
Yeah, so
this.
maybe I can
way.
rephrase this, right?
Yeah.
So like during the process of training, what we're doing is to use the visible information, right? So let's see, for example, here, you see this corner, you see that's like, let's assume for a second that you only had 2 bands, right? To this data set that we're dealing with. So that's band TA and TB, all right? You see that for this guy over here, I'm removing all the information, both in space, because the patch is being removed, and across the bands. So like, it's also like across the layers, right? In the process of training this model, I'm gonna force this model to make its best guess, right? Given the visible information for that patch in space and across all the bands. So like I do not have any dependence in terms of like, oh, I need to make sure that at least one of the bands is still visible during training. I can remove the whole patch altogether and force the model to make a prediction based on the other regions that were preserved. Okay, of course, right? Like if you remove way too much information, and that's essentially like the masking ratio, which you guys are going to have the opportunity to play with, right? If I say that I'm going to remove 50% of the patches, okay, like there is a substantial amount of information that was dropped there, right? If I say that I'm going to remove just 5%, that's almost trivial, right? A simple linear interpolation at the pixel space could make a good prediction there. If I say that I'm going to remove, for example, I have seen people doing that, like 95% of the patches, right? And usually people do that when you have like many layers. So like you have so much redundancy across all these bands that you're collecting, you can still train a model to do that, you know? So like you just make the task harder. If the model is capable of learning with such a hard task, that's the most meaningful model that you're gonna get there. So like push the model to like to the edge if you can. Yeah. Right. So like the MSE is just. Mm-hmm.
You have spatial entities. So let's say
Mhm.
they're objects, like farms or buildings.
Right.
You know, so then you can calculate so many MSCs. I mean, you can calculate, for example, MSC if you estimate the same number of trees, same number of buildings.
So what you're describing there, right, would be closer to perhaps what you would say the retrieval of the information or the content of the image, right? What we're doing here is the retrieval of the pixel values or like these numbers that are in these matrices in space across bands, right? There are models that are trying to do exactly what you're describing there, and we're going to see one of the fine-tuned models that do exactly what you're asking for. Right. So yeah, you'd be retrieving. Mhm.
How many buildings are on the bottom?
Mhm. Right. So like, yeah, is essentially what you're describing there. We'd have to change the loss function to be, instead of MSE, something else that we call cross entropy. So like the entropy that's associated to the classes that were detecting that image. And we have models to do that as well. So like the entropy, it's label dependent, right? So like that's based on as many labels as you have. But what, yeah.
Boundaries of the field things.
Mhm.
How do you decide them?
So for example, for each,
What's the response problem?
yeah, easy, you know, the each pixel can have as many labels as you want, right? As long as the labels are separated by the bands. So like, let's say that you have one band that's just like encoded for one type of information. So like the first band is going to be just like crop classification, right? Let's think that. The second band could be just straight up RGB. The third band is going to include as many informations as you want, right? Now, when you're doing cross entropy there, right? I care about the retrieval of the information in terms of like the classes of the crops that were detected for that image. You can assign higher weight to the specific layers if you want. And that's the beauty of like being able to adapt these models for a specific application, but they are highly flexible. So like if you want to prioritize one type of classification versus the other, if you want to do cross entropy in one layer and like mini square error for the others, you can do that as well, as long as you know where you have to adapt these models. But like the pre-trained version of this model, which is what we're going to be playing today, is based just for like pixel level reconstruction. So like there are no classes associated to it. Therefore, there are no like weight in terms of like how you dissociate buildings from forests. It's just like the retrieval of the pixel value. Okay? Questions? Mm-hmm. You can make inference for other bands. Yeah, you can. But yeah, so like you have to make sure that your input, the way how you're giving it as input to the model, has 6 bands. But you see, for example, here that you can fill up the bands with placeholders. See? Yeah. Right. So like you can just give the missing layers in terms of like empty values and then make inference with your model. Right, but notice one important thing, right? So like I said that like to train a foundation model, you need a lot of data and resources, which like usually is not done by the user of these models. What you're gonna do is what we call zero-shot learning, right? So like you're just gonna use these models to make inference on your own data and perhaps fine-tune it for a specific application. If I'm trying to classify like what these pixels correspond to, right? That being like buildings, forests, roads, water, and whatever, right? So like from your end, you don't need a lot of data, which is the beauty of these pre-trained foundation models. Is that you decrease by a lot the burden on you on like curating data. All right? Questions?
Please use the microphone when you pose the questions so the people cannot hear online.
Yeah.
One quick question. So on these pre-trained models, if you want them to use them, what can you say about accuracy for them and basically reliability and extending them as well? How would we go about that?
The accuracy of the pre-trained model?
Yeah, if I'm doing science with this, I also want accuracy in the end and know about bias.
Right. The accuracy overall, it's associated to like having labels, right, to this image. So for example, you can do the accuracy assessment for your own data set if you want, right? So like how this model that has been pre-trained on like the NASA data set, right? So like this HLS data set, how is it performing? That has been benchmarked. So like it's fully described in their paper. But what really matters is how this model performs to you once you don't have all the data sets. So our friend here said that she only has information on the visible spectrum, right? She doesn't have the infrared one. What's the accuracy of this model on my own data set, given like what are the things that I care about? That's an assessment that you have to do with your own data set. And then decide if you want to fine tune this model or not. Okay?
Yeah, my question is kind of in the same direction because you explain about the kind of the source of this idea for the foundation model, and I think it makes more sense for textual data than for image, because with text you really have a kind of a sparse representation where you can derive and do, for example, all the operations related to deep learning and transform back to the text, right? So, and here we are basically using it as a kind of a advanced PCA, right? You are doing this compressed representation. And my question, it's more like, in your opinion, do you think this it's kind of really useful for applications on the Earth observation data? Because, for example, in the paper, if you check the accuracy between this foundation model and a regular UNet, it's about 3% higher, right? And if you check some classes forest, it's better in the UNet than in this in the foundational model. And of course, I understand what you're saying, because this model should be trained by, I don't know, some big organization and big company with a lot of resource. But in the end, we still need to use this to do the prediction and training our pipeline, right? Mm-hmm. And also, it takes a lot of resources doing this large scale foundation model. So I think how you see it, it's really, I understand this compressed representation, and we are evaluating now. This is pretty new. But in your opinion, do you think it can really make a difference and help, for example, because in the end, we still need to use labels. We still need to use it as input to kind of derive some real application, right?
That's a great question. Yeah. So let's take it by parts, right? So what's the usefulness of a foundation model, right? Let me try to find like a allegorical example here. For example, if I'm trying to tell you like, I would like to build a car, right? I'm going to train a machine learning model to build a car. One thing, and usually that's the way how we train most of the supervised learning models, right? Is like, I'm going to learn from scratch what a car is. Like, here are the pieces that makes a car. figure out like how to build it together, put all these pieces together until you finally start to understand what are the building blocks of a car. So now after you have learned that, now design for me a Cinquecento, so like there are extra features that the Cinquecento has that you need to learn, right? What this model is doing for you is like, you no longer need to learn what a car is. Like your starting point is like a car should have 4 wheels, an engine, right? It should have doors, right? And that's the benefit of doing that, because like it has seen so many cars in its data set already during the pre-training process. So like all these things of like learning from scratch, which is like very time consuming, like you need a lot of data to do that. All of that has been taken care for you. Like when your starting point is a foundation model that you're just gonna fine tune. Okay, great. So like now the compression part, right? So like the compression, it's a means to an end, right? So like what you're trying to do is to force the model, right, to be trained with a very sparse amount of information. And because it's sparse, the learning has to be meaningful. Can you train these models by masking just like 5%? So like 95% of the patches would be visible. Yeah, you can. And the training process is going to be very fast. How meaningful is a model that is trained to learn just 5%, right? So like the compression is a means to an end. Like when you compress a lot, when you remove a lot of information and force the model to predict everything, that's a more meaningful model. And because it's a more meaningful model, right, it's going to be performing better when you do the downstream application. Now to the UNet thing, right? UNet is great, but they are trained from scratch. Try to adapt a UNet for your own application. You're going to see what a nightmare it is. The foundation model is very simple because you can just add like a regression head to it, a classification head. So they're much more flexible in that case. Okay, questions? Yes. Okay.
May I ask, Antonio, you mentioned the fine tuning of like when you already train a model, then we're just fine tuning based on our the stuff we feed into it. I'm just wondering, like in a more applicable example, is like ChatGPT when we kind of do conversation with the ChatGPT, is it something like a fine tuning when we ask them a question and we say, oh no, that's not the correct answer, and is it also doing things like that in the fine tuning?
So just to differentiate, right? So like what you're describing there, which like back and forth with the model, there is another name for that, which usually comes by the name of recycling, right? So like is the model like, oh, you didn't get it right, try again. So that would be the recycling. The fine-tune processing is closer to like what you're describing here, right? So like assuming that you know what a car is, right? I'm going to provide you some extra details about different cars. And now I would like to predict what's the maker of that car. Because now you have to leverage the features, not to describe what a car is, but what features of these cars separate them according to the different makers. So that's what the fine tuning would be doing for you in this case, okay? So like recycling, so like giving multiple attempts for the model to learn from, right? Even like a model that has already been pre-trained, right? And then there is the fine tuning, which like customizing this model, right? Doing small changes in terms of the weights of this model to better extract information about the features of your data, the data that you actually care about. And this learning process is much easier than trying to learn those things from scratch. Another example, right? So like, and I see that all the time in the summer school, right? Like, oh, I really would like to use machine learning for my data, but turns out I only have like 100 samples. Like, man, you're doomed. There is no machine learning you're gonna use for 100 samples. Like you can use something much simpler, like a linear regression and like fit a linear model here and there, GLM if you're lucky, like you're never gonna be using something like that, like training from scratch. But you can use zero-shot learning, like with a foundation model in 100 samples. Use your 100 samples to fine-tune this model. It can still learn something meaningful in that case, which like, that's why like foundation models are so important, like it's really democratizing, is that the word? Like it's making it more accessible, like using machine learning even for like much smaller data sets. Yes. You can use the microphone. Here, you can come here. Here.
The
Rich V model, if I understood very well, make it possible to go from incomplete scenes to complete scenes. So just to fill the gap within the initial images.
That's the pre-training, right? And then there is the fine-tuning. So for example, the fine-tuning, you can fine-tune this model to learn, for example, the classification of crops that are in a specific scene. We're gonna see flood detection as well, right?
Okay.
It's okay. Don't move the microphone.
Oh. Yeah, we have to use another microphone. Yeah. But yeah, so like the model is pre-trained in filling up gaps, right? But like the fine-tuning process, you can do whatever you want, like classification or regressions. It's up to you. Can you? Yeah. Okay. Now you can.
My question is, it is possible to leverage this learning from the initial task.
Yeah.
If the model is task sensitive, or the learning could be transferred to other tasks.
That's the key point here is like transfer learning, right? So like transferring whatever it has been learned during the process of doing this like masked prediction setup, right, to other tasks. So like the transfer learning is key component of the foundation. So you use this knowledge that has been learned to a downstream application, like such as the ones that we're going to see in a little bit.
So it is not task sensitive.
No, it's like I'm just learning what are the key components that build a car, just like, as we were saying before. Like what usually are the relationships between pets in a satellite image, like nothing else than that.
But if I am, for example, interested in predicting biomass,
you can do it
with this model.
With this model.
Okay, thank you.
Okay. Any other questions? Okay. So like now that we have discussed a lot about the pre-training, I hope that part's clear, right? Now we're going to discuss some of these downstream applications, which are like the fine-tuning that I have been talking about so much, right? For example, some of them could be the segmentation part, right? That we described. So like after I give you like a set of images, right? And just from the information that this model was trained on, I'm going to try to make some inference about, for example, some regions that are more prone to flooding, right? Like, do I have all the information that I need for that? Perhaps not. Like, morphological information would be highly relevant for that, right? But you can make an assessment just with the information that you have there. Another thing would be like the regression. So like you could be regressing the score of like not availability, but like how likely it would be to put like a wind farm in a location and perhaps like achieving a threshold for like required energy generation. Could be classification as well, right? So like we're talking about classifying like different crops or like classifying regions that are showing like expansion of deforestation. All these things they're like they could be fine-tuned for. In this case, we're going to be exploring two models specifically that have been fine-tuned from the original pre-trained model. The first one being flood detection, right? So like you encode an image, right, with the 6 bands that we have described before. Using the encoded representation, so like this learned representation that you have for the model, now I'm going to reconstruct the image back in the original space, but with like a binary information on it, which like there is chance of flooding or there is none, right? So that's one of the setups that this model was fine-tuned for. The other one is crop detection, right? So like here, you see that we're trying to predict specific classes, right? Like pixel-wise, right? And in this case, the loss function that we're using here was like we have binary values that we're expecting at the end. It's either floating or no floating, right? So like that was a binary cross entropy. And here we have prediction for different labels, right? Like that, I think they were using like 12 different labels, 12 different crops for this data set. So like here we are doing like classification in terms of like what's the likelihood, right? So like that's the entropy for the pixel label that I give with this model. These are the things that we are going to be covering in the tutorial in this afternoon, right? I think after the break now, because it's already past noon already. So what I'm going to do is to just do a wrap up. So like conclusion. And then after the lunch today, we come back and do the hands-on part of the tutorial. Does it sound like a plan, Piloting?
Yes, I think we have a lunch 12:30 fixed, so we still have 20 minutes.
That's
now.
not enough for the tutorial.
Yeah.
Yeah.
So, but I get everybody is overwhelmed, so maybe we make a break. But the lunch anyway is served 12:30. We cannot shift this. Yeah.
Okay. So let's do that. I'm gonna wrap it up, and maybe I show to you guys where the code that we're gonna be using is, and then we can come back and just start using it. Okay. All right. Great. So very well. Any remaining questions about the overall idea of like foundation models? Yes, please.
Yeah, actually I heard about pre-training model before, but yeah, I just didn't realize it's foundation model. I have a question is about machine learning model usually based on the model material they train, they have a lifespan of the model because the world will change. So how do you think what is the time span for one pre-training model to be used for a year or 10 years or 50 years, or we have to retrain every pre-training model every year by IBM or NASA?
So yeah, how often should you be like retraining the pre-trained model, right? So like, what's the usual timeline of ChatGPT, right? How often are they releasing a new version of ChatGPT? I think it's every 6 months now, right? Because like every time they increase the number of parameters that you have in these models, right? So you make them more robust towards like learning, extracting features from like natural language, right? Now they're multimodal trained. So like, if the distribution of your data change significantly, right? Because you're adding more samples, which sometimes it's what they do, or you change the number of parameters, you should be fine-tuning it again. In terms of like Earth observation, I think you guys are better qualified than me to answer that. Like how often you have like significant change in terms of satellite images? Like I'm not really able to answer that question, but yeah, if there is a significant change in terms of the distribution of the data set, then that's the time that you decide to do like another pre-training. Okay. All right.
I just one question, if you have time.
Yeah. Okay. Yeah. Go ahead.
Cool. Just one question regarding can I quantify the uncertainty in those model predictions somehow? Like, let's say with the flood detection, can I just say with which certainty or probability I have to estimate that a pixel is flood or not flood?
Right. So, for example, right, we said that we're using binary cross entropy, right, like for the flood detection part. So what it does is to assign probabilities over the classes, right? In this case, it's binary. So like you have probability of being 1 plus the probability of being 0, summing up to be 1 overall, right? If you have a probability of being 1 of about like 75%, 60%, like 1 being floating, right? So just to specify, like you can decide where you put this threshold, right? So for example, you can say that things that they have probability below like 65 should be labeled as like a third category, which like undefined or like not reliable or whatever you want, right? The output of the model by default is like there's gonna be floating or not, but you can definitely adapt this framework to do any type of classification you want.
Okay, cool. Yeah, that answered my question. Thanks.
Yeah. Yeah. I think you need to turn on the microphone. Yeah.
Can be used this model to predict an image with more resolution.
With more what?
Resolution.
Resolution? Okay, that's a good one, right? So like we're just talking about the distribution of the data set, right? So what does it mean? Let's say that you make a dramatic change in the data set, like this data set, not this one, because that was like global level, right? But like what most often you see is like, oh, I'm training my model with all the data that's coming from the USA, right? Will my model perform well when I start making predictions in Russia? Chances are that not, right? You don't have the same distribution of the data sets. You can try to account for like how you're gonna normalize your data, right? but like chances are that you're going to see a very reduced performance of that model. Now, other types of changes, resolution is one of them, right? So let's say that the model was trained on a specific height, right? Like where these images were collected, right? So like the height changed. So like the size of buildings, let's say that the model has never seen a building that's larger than 50% of the overall image, right? Like it would be the equivalent of this model, this building. It's a regular looking building, right? Now I'm gonna zoom out a lot. So like the height of the collecting the image change. So like that same building is now like a teeny tiny dot in my image, right? Enough to not even be recognized anymore. That could be one issue. The resolution goes in the same line, right? If you change the resolution dramatically to the point that the things are not even recognized as belonging to the same objects that the model was trained with, that could be enough to completely break the model. Yeah, so like that's something that's very important to consider. There was one more question here. Yeah.
Somebody still, there it is. Okay, so more of a hardware than a software question. So you have learning and you have inference. They both may have different hardware needs. Let's assume that we take inference for now. Let's say we have a model that's trained and we as users want to use it. What is the optimal hardware, or how do we find the optimal hardware on how we want to do the inference, and what should we pay attention to? So why?
Right. Yeah, that's a great question, right? These models, their natural environment, that's where you'll naturally find them, is living in GPUs, right? So like, and the size of the GPUs that you need to train them, it's correlated to the number of parameters, right? So for example, you don't train, for example, GPT 4.0, right, in a single 40 gigabytes GPU. You need a farm of these GPUs for you to be able to train those. When you change that to just inference, right, these models, because all you need is basically just the encoding part, you don't need to the decoder, you can run them in like more commercial GPUs. So for example, these PreTV, right, when I did the fine tuning, I was using just a 16 gigabytes GPU, which is like very accessible to most people here, right? You can even do inference in CPU only if you want, right? So like, is it the architecture wise proper for HPC? I would say no. Like it's very like not high performance friendly, right? You're gonna see that it's not even using all the CPUs that you have in your computer. But this kind of change you can do yourself basically. Yeah. But yeah, if you're just doing like inference, that's very hardware friendly overall. Great. Other questions? Yeah. Yeah, the microphone, please.
If I understood correct, we can use different resolution as long as the object is recognizable at the same size, but I don't need to change my data to the same grid to be able.
So there are some tricks that you can use, right? Because like the model was trained so sparsely, right? What you could do to perhaps like try to bridge this gap in terms of the resolution of the image is to do upsampling with a simple interpolation, right? So like there are some tricks that you can do at the pre-processing of the data part, right? That can try to bridge this gap. But the overall question here is like, by doing so, am I going to change the distribution of the data set enough for the model to just not like be able to comprehend what's in that image, right? So like, that's the only concern that you need to keep in mind.
Okay, thank you.
Mm-hmm. Yeah.
So if you take the large language models like ChatGPT, they have a really large context window. That's why I was able to upload a document and then ask, hey, what's in the document? Summarize it. What is the context window here? Like, or does it have a context window on how much information I can add it in the context window if it is available?
Right, that's a good question. So models that are like trained for language purpose, right? They have to be very flexible in terms of the number of tokens that you need to handle, right? A model that was trained for image doesn't have as much flexibility in that, right? Because like you're expecting an image to have like a specific number of pixels to start with, right? So like when you have an image that's bigger, what you do, and that's something that you're going to see in the code, is to crop that image. So you can have like this moving window that's like make classification all over the overall area that you want, but then you have to stitch it back together, right? So like, but there is a dependency in terms of like what's the size of these inputs. So yeah.
That means I should know the maximum size.
Yeah, that's a parameter that you have to be controlling for. Yeah.
Okay.
In the process of like extracting the tiles that you're gonna give as input. Yeah. Yes.
In the text example that you had in the beginning, we started with the word embeddings, right? And then we had the question of how does this work for images. In this case, what did they use to embed the images? And then when we fine tune or use your own data, do we have to use the same, or how does this work?
Oh yeah, so like the data, the part of like the data engineering part, how you're gonna process it, right? As long as you have the same dimension of the image, right, and the 6 layers that you're expecting, in whatever way you're gonna achieve that by doing upsampling of the resolution, you're using a simple linear interpolation, filling up like layers that you don't have with some like dummy placeholders, like masked values, right? As long as you do that, you don't need to care about the actual architecture in terms of like how the encoding takes place. But just to answer your question, the encoding used by the masked autoencoder, right, which is the framework that the PRITV is using here, is done with CNNs. Okay. Okay. Conclusion? Yeah. Yeah.
Well, you tend to say to everyone when they ask you a question, that's a very good question. So I think we need to recalibrate you. You're a bit overfitted. You're overfitted.
Overfitted for a quality of question. Yeah. Yeah. My classifier for quality of question is very low, as you can see. Yeah.
Well, depends on what your loss function is, right? If you're trying to maximize engagement, being positive might help.
Yeah. Yeah. I'm doing reinforcement learning here. Like, yeah. Good boy. Yeah. No, yeah. No, yeah, I appreciate the questions. I think that makes like people more engaged, and like the question that someone makes usually is someone else's question that they just didn't like have the courage to ask. So like I really like that. Cool. Okay, yeah, sure.
One last question. Does this kind of model work without any kind of input, like generating random
generative
images?
Model.
Yeah.
Okay, it is a good question. So yeah, these models, they are very context dependent, right? So like if you give nothing, right, what it's gonna do is to just like imagine some garbage, right? So like it's gonna be a completely nonsensical image that you're gonna get as output, right? So like I would just say that the model would not work for you. You'd get something as output, but it would just not be good at all. So yeah.
Anyway, it would be interesting to see the limit of what's the minimum size of the input that you can give and get, let's say,
How much masking you can do. That's an experiment that you guys can do this afternoon. So like I'm gonna show you how to control for that. So you can see like how much can I drop, right? And still get something that's like meaningful in the output. Conclude? Yeah, sure.
We have an example. It's on the land cover classification. And we had like a couple of millions training points and use random forest. And then we switched to support vector machine and we did only 6,000 points and we got the better performance.
Okay.
It's not that because support vector machine is something magical, but I think it was the overfitting.
Yeah, so that's another thing that we try to discuss extensively during the course, right? Which is like when you provide too much information, right? You don't regularize your model enough. The model is very prone, right, to finding shortcuts that are going to maximize like performance of the model, right? So for example, signs of overfitting when you're training a model, one of them that you can control for is like what's the performance on the training data set versus the performance on the test data set, right? That's one thing that you can do. Another one is to make the task harder. If the task is harder, it's very hard for a model to be able to overfit on it because the data set's not overcomplete, you see? So for example, what would be the case where the model is gonna learn, right? It's gonna reach a really good performance, but it's gonna perform poorly like in new data set. In this case, it would be if you train this model with a masking rate of just 5%. So like the data is highly overcomplete because like neighboring patches, they almost have the same information most often, right? If you're like have a satellite image of a forest, all the patches are just green, right? So like you have to force the model to learn something that's meaningful by making the task very hard, right? In the case of like moving from random forest to a supported vector machine, most likely you're using stronger regularizers there. That would be my guess. My guess would be that like that SVM had stronger regularizer. That's not to say that random forest was worse. Perhaps it was just not using the proper sets. The setup was could be is likely better. So okay. Conclusion. Okay, so conclusions. Foundation models, right? Like as we said, they are like these massive models trained in a lot of data set. We hope that these models, and that has been like the rule for the machine learning community, right? They are trained for the people with resource and access to data and then made available. So like this has to be an open source effort. Even big companies, they do that. Of course, like they have profit as the main driver, right? So for example, ChatGPT, what they do is to release much older versions. So for example, right now you can use GPT-2, right? Like it's all the weights are public available. But then you have Facebook with Llama, right? You have Gemma, I think, right? Like so some of you guys are already using that become available like as soon as they release the things. So like foundation models until now has been very much like an open source effort there. The advantage, right? The starting point, as I try to like emphasize that, is like a model that already has a pretty high level of understanding of your data, right? Which you can leverage for specific applications, which like the cool thing about using foundation models. You can train this model that has seen like understands everything about satellite image to classify specific things or like to quantify things that you care about, right? In these terms, right? Then you have like the few shot learning. So for example, if you just want to make like some quick inferences about the data sets that you have, just like completing an image that has been corrupted by shadows or like clouds or so that you'd like to remove, you can make specific classifications out of it, which is the fine tuning process, right? For the tutorial today, like we're going to be playing with some of these fine-tuned models, like for flood detection, crop classification, and this few-shot learning part, which is like the completion of an image that has been corrupted by masking, okay? And then I'm going to give you the code on how you can fine-tune these models to your specific application. And then if you want to dive in this adventure, like in the afternoon, we're going to work on that together. But what I really hope that we manage to achieve together is at least for you guys to learn how to run inference with these models, because everything else comes from like learning how to interact with them. So like we're going to be working on that this afternoon. So break, okay? Again, I know that this is a lot to digest. I hope at least like the overall idea you guys managed to grasp here. There is quite a bit of like background information that was not able to provide. So like, please do make use of this resource that we have available in the Spatial Ecology website, okay? And consider signing up for the course next year, too, because like it's a lot of fun. As you can see here, like that was a picture that we took in one of the sightseeing places in Matera, where we also have very fun barbecue, like in the last day of the summer school. So it's quite an experience for the people who have been there. I think they can verify that like it's a very fun environment to be learning at. So okay. And okay, so then we are back. Oh, exactly 12:30. Wow. Like then we are back for the hands-on tutorial in the afternoon. Okay. Cool. Thank you. Okay. So I'm gonna stop this. Sim, sim, a gente vai colocar no site do Spatial College. Na verdade, você tá no Discord, tá? Então, acho que o Pepe já compartilhou os slides, tá? E eu acho que esses recordings vão ser compartilhados pra galera depois.
não. Obrigado.
Olá.
And it's mounted. Russland's comment was certainly not optimal to do because mounting my axis. And everybody actually anyone anybody who's a guardian can get into the benefit of right? Yeah, I think you can go into the no, I mean, but okay, but that is actually that's not any part of the project. Yeah, it's so it's because I'm not no, before I had exhibition. Now so just did I didn't have graphics before. Yeah, I think it should actually the same way. That's my story. It's basically it's time to be as well. The open source network is way. I couldn't say this, but yeah. I mean, you can talk in Spanish. Just like for example, my friends follow me. You want like to take a signal I mean, outside of safety, but assuming that you can start something after like also 3 years. You know, so this is why I think I think a lot of people say because that's what's not speaking with that. And they got it's not really the biggest burden share, and then you need to like get an idea of the brand. I don't know what's the secret in one of these burgers. They can get one of the some of the actually. No, I think I don't think before I get out of that nothing. And then go something for people pull their way from the other channels. When it could be clear, but it's just like could have just gone to the outer shell. But and you have like I think half the projects are already ready to download to download so that you think. Technically, a little bit of the library will work out, but like maybe that's like that's what you do now. That is how fast. That's why you can do that. Like if I'm thinking about it's like yeah. Oh, I realized that I'm not really trying to. Like I also still have to like 2 fingers. Now. What is the first? How they get it's signed by the exposed. Right, essentially. For example, you could say like in a very serious housing, like my I don't know. People. Class. I enjoy. Right, that's very unstructured. Like, at least it was like language, natural language. Those are the orders who think should be domains. Like, if you mess up the data set, it's really. Right? That they're meant for like learning. Powers from inducing features. Oh, that's a key difference. I mean, usually that's kind of just provides children, right? Remember that's like now data by like projecting like the information layer. Yeah. If you can do that.
Ja, aber das ist das. Ja, aber wir machen das nicht wahr.
Yeah, go on. Yes. Very hot. That is after telling you will have like an hour probably like defense. He will do not. No. You have What's the definition for opposite? Just gonna be. Yeah, and into this part. Yeah, perfect. It's for the slide as well. Well, just a second. So, down here. And then what computer do you use? My yours. So then you need to be on the Teams and everything, right? Yeah. You're connected and stuff. I need to bring on my team. You need to bring on the team. Yeah, I think that's Teams, right? I mean, yeah. Not sure how else, or we use this computer, but then you can't do. That would should also be okay because I think we got a new place. Yeah, and then maybe we should just show the chat. Yeah. I think it's also fine. And then left it open. Yeah, if you want, I mean, we can also have this in two. We can have them parallel and scroll both and show them that this is kind of the same. Not sure. What you think? Okay. Then we would have to also like download the HTML.
We don't have to download.
According to me. I don't have to download. Yeah, we have to download. Maybe we can just hold it. Also, there. That's small. Yeah, why not? It's a Windows. I don't know how to use Windows. Git clone should be the same.
Yeah, maybe they don't have Git.
Don't even have to sign in.
Mm.
So it's good clone, you don't even have to
Where is the repository?
double that point.
sure we can find it. I don't think we can find it.
Yeah.
Down. Oh, let me see. I don't know how to use Windows. Where's the terminal?
Control.
CMP.
Let's try. Anybody use Windows here? Terminal. Oh, the Windows type terminal. So in one there.
Oh.
Terminal. Oh yeah.
I knew it.
Use the
Is it finished? Why are you so slow?
yeah. Check it first.
Have I extract? You see. Okay. I think I prepared. But I have to show the code. Yeah. I open on the tab. I hacked the tab. This is yours. This is yours.
So we just need the presentation.
Yeah, I think.
It's not like complicating the problem.
Maybe I can see if I can code. Oh.
Yeah.
Hey, Military.
Can you approve me to join the room here? I sent a request to join the call, so I think you need to let me in. All right. Let's do the hands-on part. Okay, let me try to share. Right. Okay. Are we all here? Can I start? Okay, so back to the second round. We are gonna do some experiments with PreTV now. Okay, so how is it gonna work? Better? Okay. All right. So for educational purposes, I'm going to be running these on a Jupyter notebook, okay? But for you guys, we have prepared a script in Python, which you can find under this path. I think I can copy this and share that with you guys on Discord. Is there a proper channel to share stuff like this, Pepe? Coding. Okay, so that's the path to the Python script. Okay. So you're gonna see that there is a script there called exploration. Okay. So yesterday, Francesco introduced the process of preparing this apptainer, right? So like, let's all thank Francesco for the amazing work that he has been done for us. So like, thanks to him, we don't need to do that. But also, if it doesn't work, it's his fault. So like, it's important to. Yeah. No, it should be fine. So like in this script, if you open it, right, this exploration there, of course, you don't have writing rights on it. So like if you want to modify this script, which you should do, right, you have to make sure that you make a copy of it so you can have the writing rights to it. All right. And everything that's in this script is exactly the same stuff that I'm going to be explaining to you guys on my Jupyter notebook. I'm just going to use the Jupyter notebook because then it's easier to see the plots that follow. All right, but feel free to make a copy of this script and modify in whatever way you want. Okay, how do you access this script? So like, let's hope that everything works nicely. So like, I'm gonna SSH to this thing. So like my scripts, they are in project ML. So like if I come here, I think it's one level higher. Yeah, you're gonna see the exploration script there, right? In terms of like the package that we're gonna be using, right? So like I told you that we're gonna be using this PrettyV 100, right? So you see that these weights of this model are coming from the GitHub page. If you're curious to see the good GitHub page, you can just type PrettyV 100. You should be able to find it. Or otherwise, you can just come to the original page of this model. How many of you are familiarized with Hugging Face? Just so, okay, I see a few hands there, okay. But everyone knows GitHub, correct? How many hands of people here like has used, oh, excellent, great. So like Hugging Face is a similar principle, right? I think the difference there is that it's environments, depending on the model, you can even deploy the model from within the web interface of Hugging Face. So for example, in terms of large language models, I see that most often they have a demo that you can run directly from there. And PrettyV is not different. So for example, if you just want to see how this model works, right? You can come to the root, right? So you're going to see the IBM NASA Geospatial page there. Let me send this for you guys on Discord as well. Link to IBM NASA. In case you guys want to read more about it, I highly recommend, right? So like you're going to see like a description of the data set that was used, and then you're going to see some of these pre-trained models, which we're going to be exploring today, but on the terminal, right? But if you just want to run inference, and that's like the cool part about Hugging Face, right? You can directly come to the demo page. It's going to load the model for you. And then here you even have some examples that you can load directly, right? So like, for example, I told you that this data set has like collection across days as well, right? I don't know exactly like when these different images were collected, but you see that they are from the same region, but they have like different differences across them, right? And then you can submit this for like this pre-trained model, right? So like you could run a classification within from this demo interface here. Of course, we're going to be doing everything ourselves. So like that's just so you know these things exist. Okay. Okay, in case that you are setting up this whole thing from scratch, you'd have to do the git clone, right? You're gonna have to do like this renaming of the folders and so we can load that as like Python package, do the installation. Thanks to Francesco, we don't need to do that, right? In terms of like what you need to change here, right? So like the first thing that we have to do is to start a session, right? So like you're going to start interactive job in this case. I told you that like these models, although they are heavily dependent on GPUs for the training purpose, right? Since GPUs are complicated to allocate when you have like such a big crowd, right? Like resources on GPUs, they're usually limited. We're going to be doing the inferences in CPU. And that's okay because we're not running this for like a million samples, right? So like all the experiments that we're going to be doing today, at least at the demo session, is going to be with single images. So that's okay. Once you start moving from these to like doing global predictions, then it becomes crucial to have like speed in processing, right? Very well. So like, let's start this thing. So like right now you see that's like now I'm running in Node, right? Like within the HPC environment. Is this big enough? Can you guys see stuff there? Okay, great. Yeah. So once I have done that, now I have to start my container. Takes a little bit. So like here, as Francesco mentioned yesterday, right? You see that we are binding some specific paths. So like the project GeoCourse, it's a path that I have within my environment where I have all this stuff related to the tutorials and so, right?
Yeah, paste also this line, Antonio.
Yes. Okay. Activate container. Okay. So depending on how your bash RC looks like, you might need to do one extra step. I'm not entirely sure how many of you might need to do that, which is to write if condition in the case that you're running AppTainer. So for example, let's see here. So like what we have done here, and Francesco can give you more details since he's the head behind this operation here. What we are doing here is essentially to not load a bunch of other things that we would be loading. For example, you see that we are doing all these like specification of like software lib and paths and like Python versions and so we are just loading the container. So like everything that you need for this tutorial should be within this space. Okay. So like if you run into any issues, that could be one of the reasons. People are already stuck? It's what? Sorry? Yeah. Oh, you need, yeah. Okay, so I'm gonna paste that for you as well. Okay. Okay.
And the FI and at the hand, don't miss that.
Oh, yeah. So like, of course, there is a if condition, if there is a apptainer, right? There is a then. So like, make sure that you include the then. And the else would be the last thing that you're gonna add. So like, it's this file. So like your bash RC should end with this instruction there. Mm-hmm. Yeah, so that's what Francesco was showing yesterday, right? So like you guys have the link to the GitHub where we gave you the preparation for the apptainer that we're using for this tutorial. So like, let me just open this very quickly. Then, yeah, here, right? So like if you go to the apptainer for Conda, that's what we are using. So you're gonna see the Conda env that I exported from my working environment. So like you make sure that you're using exactly the same versions of the package that I'm using, so you can reproduce everything we're doing together today, right? So like very extensive list of packages there for you.
Oh, Antonio?
Yeah.
So should we use the apptainer we created, or we just use
No, that's what I was mentioning yesterday. So like we are all gonna use the apptainer that I created with Francesco yesterday.
So we just copy the one you created.
Just run the things that I shared with you, like to load the apptainer that's already prepared. So
Okay.
you don't need to prepare your own. Okay, so after you have done this, okay, so like the bash RC has been updated, right? There is one more thing that I need you guys to do, which is during the process of downloading these pre-trained models, right? We're gonna download that to like a cache path on your home, right? And during the process of downloading that, Hugging Face is gonna look for these folders, right? So like I want to make sure that we are specifying where this is gonna be. So like go to your home. You can do that very quickly by just typing cd, right? And then create this folder called .cache, which is what we are gonna be using. And we are also linking when we're creating the apptainer. So you see that we're looking for this cache. So like we're gonna be doing that. Okay. All right.
So sorry, Antonio, could you please repeat this bash RC modification?
Mm-hmm. Okay. Bash RC. Is everyone here? Did you guys manage to open your own bash RC? You can type cd, that throws you to home, right? To your own home. So like with your user. Now, if you want to modify your bash RC, you can use your editor of preference. I'm loading Nano here. So your bash RC should look like something like this, right? Okay. So like, should I just share my whole bash RC with everyone? Would that be easier? Okay. Okay. Ah, yeah, it's down here. Yeah, I think that's a good idea. I'm just gonna copy this whole thing. Oh. How do I copy everything? Done. Let me see.
Do not blind paste in the bash RC, if not, you are going to lose old alias. So be careful what you paste.
Thing. Just keep in mind that like if you don't manage to figure out this step now, just follow what I'm gonna be doing, and then we do that during the like work on your own data session. Like it's not worth to waste all the time just setting up this. After you have modified your bashrc, you have this .cache on your home directory, right? What we're gonna do next is to go to that folder, the ML folder that I shared with you guys on Discord. Okay, yeah, it's already there. So it's this guy over here, okay? So like, that's what we're gonna do now. I'm already in that folder, but just for the sake of completeness, CD there. Oh, I went one level higher. I'm just gonna go back one. So like, you should be in this folder now. That's from where we're gonna start the container, okay? Is everyone here? Okay. Then you're gonna run the apptainer command that I also shared with you guys here. So like that's the apptainer command right here. So like start the apptainer. So now we are in the environment where from where we're gonna be running stuff, right? So like just sorry. Right, I think that's from where we are loading the apptainer, right, Francesco? Like the Jovian, it's your user, right? Because you set up the container.
The reason is that I'm using a Docker image produced by the Jupyter teams, and for some mysterious reason, there's this username.
Right. Yeah.
Do we start from the ML folder, or should we copy that to our?
No, you should start from our ML folder because that's where we're going to be loading the container, and we are using all the same container. Yeah, all the same apptainer. Right. Apptainer, not container. Yeah, apptainer. Yeah, so like you have to do the CD to this path, right? So like the projects, GeoCore, software, apptainer, ML. And it's from this path that you're going to start the apptainer.
The last word in the command, guys, the last word in the command is conda to sif. What does it mean? Without any path. So means that it's going to look where you have this file in the location where you are. If you don't have the conda to sif in that location, will not work. Okay? So in Antonio's case, he has there, so he can run from there. But in your case, I don't know where you have it. So first search for the conda to sif, and then you run in that directory.
Antonio, could you please take a look at the comment? Paolo has an issue with the folder. I think probably he didn't create this .cache. It's in MS Teams.
Yes, probably didn't create the cache.
Right. So like go back to your home directory, right? And
so Paolo, this is now for your instructions.
Yes, I'm listening. Thank you.
Yeah. So you got that part, right? CD back to your home directory and create a .cache in there. You might have to adjust the paths after you have copied it, right? But like for now, no need to copy. Yeah, exactly. Yeah. Yeah. don't have conda to CIF, you should have conda to CIF in this path. So like, you see that you have a conda to CIF here. So like, if you're in the right path, project, GeoCore, software, obtainer, ML, you should see a conda to CIF there. Okay. All right. Moving on. How many people are still stuck? Just so I say if I should. Are you stuck? Ah, okay. How many people are currently stuck? Okay, we have 3 people still stuck. Help your friend. If your neighbor is stuck, help him. Yeah.
Note that the CIF file, the CIF images, is a read-only stuff. So you can share easily with the other users and use at the same moment. Huh? That's no problem.
Yeah. Okay, for the interest of time, okay. So like, if you're stuck, look at your friend's screen and let's just move on, okay? So what we're gonna do next, right? So like, first, see where you are. So PWD, okay? For the next step, you should make sure that you're like, within ML, you get inside this folder HLS Foundation OS, okay? So like, just CD to that folder, all right? What is inside of this HLS? Yeah. This? Better? Okay, let me move this a little bit. All right. Is everyone here inside of HLS Foundation OS? Okay. So this is the repository. Okay. And like inside this repository, which like the original repository that's kept by NASA Impact, right? Is where you're gonna find all the things related to this tutorial today, right? So like you don't need to do the git clone because that's already done for you. Like when we created the image, right? It's just for the sake of like you knowing where these packages are coming from. So from here, you're gonna get like these configurations, right? That specify the architecture of the models that we're gonna be using. Again, we're gonna see that in a little bit, but you start a model and then you load the weights that were trained for that model. Okay, so like that's the role of this HLS Foundation OS path that we're gonna be using. Okay, I just want to make sure that everyone is here for now. Okay, great. So from here, just make sure that this next step is working for you. You're gonna execute the Python command that starts the exploration script. Here's an example. So like, we're gonna call Python, right? Pointing to this exploration.py, which is like in the parent folder, ML, right? The parameters that come after that are the name of the model. So like for just the sake of testing, if everything is loading properly to you, specify model name, float pred, just the way as is here. And then if it fails for you, I'm so sorry for you. No, if it fails, that means that there are some steps that we still need to go over again, like on the top. That's correct, as I just typed it here. Yeah. And what's the purpose of doing that right now, right? So like you see that I haven't explained anything about the model. I just trying to make sure that like these things are working for you so we can modify later. Okay? So it's hanging a little bit because the import of this package takes a little while. This is a warning message because the torch version that we installed apparently is not agreeing with the rest of the environment. But you know, warnings you can just disregard altogether. Okay, so like if you're seeing this message, that means that the model is running. We're gonna explain what that means. I just want to make sure that you all get to see the same stuff for now. So like that's the model is starting, like the loading of the pre-trained model. Permission denied? Okay. I mean, was that in the load operation? Let me see what's the error that you got. So if you got that error message, I'm going to show you what you have to do different. Okay, so if you got that error message, okay, you're gonna see that there is a download file function that I defined, and that's all because I had to convert my Jupyter notebook to like a script. So like I didn't run into the same issues that you guys are having now, but like the download file, right, is just pulling from Hugging Face these samples that are these .tif that we're going to be using for the tutorial, right? You guys can copy exploration.py and change where this thing is being saved. So like it's as simple as that. Because right now it's trying to write this stuff to the software path, right? Where you guys don't have writing permission. So like it's as simple as that. Yeah, so like this download file, right? It's trying to download this image. Let me show you here. It's more visible, okay? Trying to download this image that we're going to be using for examples, right? Like on how you can run the model, right? On like some new samples from the data set. So you could do the same just doing wget. So like, let me do that for you guys so you can just load. Okay, here. So that's the Spain one, which I think Maria had issues with. So like, you can do the same for the others. Like you can download directly stuff like this using wget. Okay, just make sure that you don't write to the same software path because the software path apparently only the teachers have writing permission to, and that's why we didn't run into the same issues that you guys are running into now. Yeah, you can. Just have to say from where we're going to be loading this image later, right? Because like in this float one, right? Let me show the script here. That's a little cleaner. So like that's the same exploration py, right? It's just like using my editor of preference. So like in this float, that's the instruction that's failing for you guys right now. So like let me maximize this. Try to increase the font size. Is it visible to everyone? Okay. So like I'm trying to download these samples, like which are like some TIFF images from the repository, from the IBM NASA repo, right? So like what's failing for you guys now is that when you run this script, and this script is hosted in the software path, right? Which only the teachers have writing permission to, it fails because you cannot download something to that path. So like that's the only thing that's failing right now. So what's the workaround? Go to your home directory. From there, do the wget using these paths that I shared with you guys on Discord, right? So like these wgets that you see here, okay? And then what you need to do is to change from where you're loading, because you're no longer loading this from the current directory where you are, but rather from home, right? So like after you have done the wget, probably you're gonna have to do home. In my case, the geo course, teacher 02, and then this, okay? The exploration. Oh God, yeah.
Change the Python script.
Yeah, make a copy of the exploration.py. I hate tutorials. Yeah. Yeah. You know what? Yeah, just watch me doing it. Then in the work with your own data, we figure this out. Otherwise, we're gonna take forever here. Okay, so imagine for a second that the installation worked. Okay. So what are we gonna do now? And again, this script that I'm going over is exactly the same exploration.py that you have there for you. So you can modify once we get that thing to work for you in whatever way you want, okay? So like in terms of packages, what are we using? Like classic packages that you guys are probably familiarized with. So like import OS to deal with like paths and stuff within your environment. Torch, that's PyTorch for those who are not familiarized with the lingo. So that's the library that we use to construct like neural networks based models, right? Matplotlib for plotting, like NumPy to deal with matrices, Rasterio for like plotting stuff, and so. And then finally, we have the masked out encoder, which is this framework like that's gonna give us access to all these intermediary layers that implement this thing that we discussed before, right? So like that's the masked out encoder that Prithvi is using, which is exactly what Facebook designed, right? So like that's the package that you're importing there. Okay, so here there is some information about how you're gonna handle some missing data, right? So like in case that you have these things like with -99, which I think is like a placeholder for missing data in this data set, you're gonna be replacing by a constant, like very close to 0, all right? Everything below this is just for the sake of like how you're gonna extract the information from these samples that you're loading, right? So like you guys remember that I said we are using just 6 layers, right? For the samples that we're gonna be running inference. So in this case, if you have more than 6, you have to first see which ones are the layers that this model requires. In the case that like when you start using your own data set. But for now, you don't need to worry about that because all the samples that we are loading, the first 6 layers are already the ones that we need, which is blue, green, red, these infrared stuff and so. Okay. Another function to just like do the plotting, so like clipping some values of these matrices that we're going to use for the plotting later on. And this is the plot image mask reconstruction. So like if you guys remember the output of this model, right, is going to be the reconstruction of all the patches, right, including the ones that are visible, right? So it is effectively running a prediction for the patch that's visible, right? So like you could plot the prediction of that visible patch, right? The one that you gave as input, or you can simply replace that prediction by the original data, right? Which is what I prefer to do. So like, that's what I do here. So like from the predictions, right? I only replace the images that were predicted for the masked region. So like, this is the identification for the masked patches, right? For those only, I replace in the original image. So like, the visible patches are the original patches instead of prediction, and then I just include in that image the predictions from the model output. That's the only difference. Okay, now to the interesting part, okay? So like, how do we load these models, right? From the Git clone that you did, right, that we did for you, which you can reproduce in your own environment, we're gonna load this pre-trained model, which like the previous pre-TV 100 million parameters, right? How do you load that in PyTorch? So like, you call the torch load, right, for that set of weights, right? After you have done that, now you have to assign those weights to your model, right? Your model is defined according to this configuration file that's coming from the pre-TV 100 config. What is in this file? It's gonna look like this. Let me show you very quickly. Yeah, so like, you guys remember that we were talking about like how many transformer blocks we had, right? Like for encoder and decoder, like what's the resolution of the image, what is the dimensionality of these latent representations, right? So like, all this information is specified here. So for example, number of input channels is saying that 6, right? Number of heads. So you guys remember that, like for the transformer, the vanilla transformer, we had 8 heads. So you see that this guy is using 12, for example. What is the size of these patches, right? So again, the patches are essentially the size of these squares that we're using to parse the image, right? So the input size of the image is 24 by 24 pixels, right? And you're gonna be parsing that in small patches of 16. So like, we're gonna have like these patches of 16 pixels over the image, okay? Some normalization that we need to do, like again, to try to bring these new samples to the distribution of the data set that was used for training the model, right? You guys remember that there was a parameter with respect to how many patches we removed from the image during training, right? This model specifically was trained removing 75% of the patches, right? In this case, like 75% of the information contained in the satellite image are removed during training, okay? So that's the type of information that we're gonna specify through this YML that's being loaded there, okay? All right. Here we create the model, right? So like, we're saying that's a model from the class masked out encoder, which assumes that all this structure that we are defining here is it's being loaded according to this config file, right? And finally, we get these weights from this pre-trained model that we have specified here in this path, right? To be loaded to this model. So now we have a model with the architecture that was used for training and the weights that were used for the pre-training. So like, now we can run inference on this, okay? Let me run this. I think I haven't done that yet. So if you do print of this model, you should be able to see all this information, right? So like, that's the description of the architecture of the model there, right? So you're gonna see like the QKV that we described before, right? You guys remember that's how you project these patches to these latent representations, QK and V, right? That we use to learn the relationship between the patches that are part of the sequence, right? The patch embed, you guys remember that the VIT was using a linear flattening of the patches and then using a linear projection, right? Like the masked out encoder use convolutional neural networks, which is better, right? Because it accounts better for like spatial information, okay? And then we have a bunch of these blocks. I think we have 12 of them. You see 9, 10, and 11. Because the counting starts at 0, right? So like, we have 12 of these blocks for the encoding, right? during pre-training, you also have the decoding, right? Because you want to make sure that what you have in the output, let me zoom in. What you have in the output mimics the input before the corruption, right? So like you do need a decoder for the pre-training, but like once we move away from the pre-trained model and start using the fine-tuned model, we no longer use the decoder for anything, okay? But it's there in case that your application could benefit from it, okay? All right. So now to like some of these images that we're going to use, right? So like here you see another image that I'm loading directly from Hugging Face, right? So like you see that I'm specifying the path to Hugging Face here. Was there someone saying something? No? Okay. So like we are going to load this image. So the shape of this image, right? It had 6 channels, and then the image was 500 by 540, right? Which again, according to the specification of my model, which I already closed, right? The input size that this model is expecting is 224 by 224, right? You could downsample the resolution if like you actually care about running inference in one shot for the whole thing, or you can crop and then do this thing that we described as like the sliding window over the image and then just combining that afterwards, right? In this case, I decided to go for the cropping, right? So like you see that I'm cropping this image from this 500 by 540 to just the top left 224 by 224, keeping all the channels, okay? So that's what we're seeing there. It should eventually, okay, yeah. So that's the image in 224 by 224, okay? So like the first steps that we can do, right? So like, let's see how this model would perform if we remove randomly like some of these patches, right, from the image and try to perform a prediction for it, right? So that's what we're gonna do here. So like this image needs to be normalized to the distribution that follows the distribution of the original data set, right? So that's the normalization step that we're doing here, right? So like you guys remember that I had the information on what was the mean in standard deviation of the samples that were used for training this model. So like I normalize my new sample, my new image to follow this distribution, right? So like to make sure that the mean and standard deviation is matching this. So that's what the pre-processed image is doing for you. So you see that I'm removing the mean and dividing by the standard deviation just to make sure that's like, okay, this looks like a sample that came from the training set of this model. That's what we do there. Now we run an inference, okay? So like after the normalization has been done, right? We're gonna run an inference with this model. So like we drop all these regularization things that we add to the model, like for those who are not familiarized, some of the things that we add as regularizers to a neuronal network is like some spontaneous dropout of some of the nodes that compose that neuronal network. So you remove that during the inference. And then you have the masking ratio, right? This model was trained with a masking of 75% during a training, right? Which is specified here, right? So I could be running inference with 75% of the information removed, right? Here, let's see how this model do with just 50% of removal of the information. So like, call that, okay. You see that the output of the model, right, is 196 for this first dimension. So where is this 196 coming from? This is the number of patches that we have, right? After we have split this image that was 224 by 224 in many little squares of 16 by 16. That's a total of 196 patches, right? So you have here the number of patches that were extracted from the image, right? And this here is the size of this patch. So like after you have done the prediction, you have to do the reconstruction back to the original shape of these patches, right? Which would like to be 16 by 16. And that's what we do in this unpatchify function that's included in the model, okay? So here's an output. I can just run this again just to see. Okay, it's slightly different, but yeah. So this was the original image, okay? And again, all this stuff you guys can reproduce in that exploration.py that I created for you guys, and we're gonna figure out the installation later, I promise, okay? So like, for now, just believe me that these things, they work the way how we're describing. So that's the original image, right? This is after the corruption, by removing the patch. So what's in black are the regions that were removed, okay? And this is the reconstructed image, right? So again, these regions that are visible, right? They are preserved here, right? So like we are keeping those. So we are not looking at the prediction of the model for the visible patch. The regions that were masked, those were predicted, okay? So for example, if we narrow like in this region here, you can see that there is a little bit of discontinuity here. I don't know if you guys can see, not that much there perhaps, but yeah, there is discontinuity, right? It's a little bit more blurry, like in these regions than compared to the visible ones, right? Can you guys see that? So like, yeah, is the prediction perfect? Absolutely not. You know, like it's very blurry, right? Which it's a known caveat of like predictions. It's like you don't get really sharp things. Can you make this better? Yeah, absolutely, right? So like there are several things that people have been adapting. So for example, to include a diffusion step in this, right? To like get sharper outputs in the end. But for our purpose here, we don't need to explore that.
Sorry, Antonio.
Yeah.
The prediction takes into account also the period in which the image was taken. Because, for example, here I see the crops, so probably if in the same period there are the same crops, probably the prediction will be better.
Right. So this task that we're using right now, right, is using as information just the visible patches, right? So like that you're talking about temporal dependencies, right? If you understand the question.
The question was, yes, we have masked a part of the image. So the program is providing to suppose what it was below the patches we have applied. But in this substitution, it takes into account also the period in which the image was taken, because in this case, probably it would be better because in the same period there are the crops. Instead, he is probably substituting some the images in a period in which there weren't crops, so it is fading in substituting the fields, I guess.
Right. I think we can. I think Pepe has a comment. Yeah, go ahead.
Concerning, we are watching only one image, so we are not taking into consideration any temporal change, just one image. So the prediction is based on the guess from the algorithm to check one image.
Single image, yeah.
Okay. So there is no any agricultural changing, shifting or whatever. So it's just based on the algorithm from that image.
I didn't explain very good my question, but we can skip, and I don't want to steal too much time. Sorry.
Yeah. Feel free to drop your question at Discord, and then we can address that later as well. Okay. But like, what I would like us to be able to discuss here, right, is like where this model fails the most, right? So like regions that are a bit more homogeneous, like this one, right? The predictions are not terrible. But look at this one that had like higher level of details, right? So like notice that this region of the image was the one that was removed. You see that there is a severe degree of hallucination happening here, right? So this model was not capable of making like an accurate prediction for this specific region here with high level details. Like some other things that you could see with this model is that, for example, if you block completely a whole chunk here, right? Like say that there was a massive cloud that's emitting like 25% of the image, it's going to be very much just hallucination that you're going to get from that region, unless you have similar images that were collected from that region across time that could potentially like be helpful for making predictions for what should be under the omitted region. Okay. So yeah, there is a limitation with respect to how much detailed information can retrieve with such methods. All right, so that is perhaps the least interesting application of this model, right? Where you're just like have a very sparse sampling from that region, and you're trying to make inference about other regions that, like other patches in this case, for which you don't have information, right? Let's see some of these fine-tuned models, right? One of them that we discussed was the flood segmentation, right? Which is the prediction of this sort of a binary mask, right? That tells you in which regions, according to just like the 6 layers that you're using as inputs, right, are more prone for flooding. So for this step, what we're gonna do is to use this model in a slightly different way, right? So like now that we're gonna use a fine-tuned model, I'm gonna show you here how you can download this fine-tuned model directly from Hugging Face, right? You guys remember that here you had this demo, right? Where you can play directly with this fine-tuned model. The same way how you can do this here, you can download it locally. You can download this model locally, modify it in whatever way you want, right? So like in the case that you're gonna do the fine tuning, and we're gonna see that in a little bit how you can do that, and run inference for like a given checkpoint, right? So like this first line is telling you, specifying what's the configuration that you're gonna use, right? So like that's very similar to the .yml that you had on the top. Here we are saying that we are gonna use the weights that were associated to that training session, right? And then finally, this initial segmentator, right? Segmenter, that's, yeah, segmenter. It's specifying this architecture right here, right? So like, it's basically saying that we're gonna use just the encoder part, right, of this trained model. And then I have these extra layers, right, which are coming from this Sentinel flood detector that are also fine-tuned for this specific application over here. Okay, so that's just creating a new instance of this fine-tuned model using this configuration that was specified up here. Okay, and that was also the message that you guys saw in my screen and not on yours yet, right? When you're saying that, oh yeah, this model is downloading, right? Like loading the checkpoint that has these weights that were trained for the flooding task and so. And that you're gonna see on your own environment in a little bit once we finish the installation stuff. All right, so like if you run this, okay, so the imports were done. Now this is loading the pre-trained model. Okay, load the model there. So now that's where you guys were getting an error message because I was trying to load this image, right? That was downloaded from their Hugging Face for the inference, right? And again, the issue was that it was trying to download to software from where you cannot do this download. Oh, actually, I think these images are already there, right? Ah, perfect. So what you guys would have to do is just to comment this out. So like later on, yeah, so that's what we're gonna do in a little bit. We're gonna remove these lines and just load the things that are already saved there. Okay, that might be easier than I was thinking. Okay, but let's run the inference for this sample, right? So like now I'm gonna load the sample, plot the shape, right? And then we're gonna run the inference. Notice that for this model, right, look at the input shape, 512 by 512. So like this model was fine-tuned with a different image size, right? So like when you're running inference with this model, it's important to see what is the specification for this model, right? For the pre-trained model was the 224 by 224, but for this one, the fine-tuned model for like the flood prediction was 512. So like please make sure that you're like formatting your data set, right, to match the expectations of the model. So this is how this image looks like, right? Now we are going to run an inference with this fine-tuned model. For this image. It's taking a little bit. The shape of this output is 512 by 512, right? This should be a binary mask. So let's just see what's the range. Just to confirm. Yeah, so like it's a binary mask. As expected, the maximum value, it's 1, right? Where 1 is the region that's prone for flooding, and 0 for the regions that were not. Oh, wow, awesome. Oh, yeah. Pepe, you uploaded the notebook, right? Okay. Where did you put the... was it in a different one?
The logistic.
Ah, it's logistic.
Yeah. Then go up.
Oh, no, it's in...
Yeah, just up.
Ah, okay.
Yeah, over there. Bravo. Yeah.
Okay. So now we just look all together on this saved one. Okay, so running inference for this guy now, right? So here, what I'm exporting now is the original image, right? And where we had 1s and 0s for this specific image, right? So like those were the regions that were detected as more prone to flooding, given this model. And this is the overlapped region, right? Can we validate that, right? Unfortunately, I cannot. I don't know about you guys, right? But the next step of this tutorial would be essentially to allow you guys to download an image for your region, right? Where you know where there is like flooding or not, or like even some specific types of crops. So you can validate the accuracy of this method on your own, okay? This process, it's then repeated for a different image. That's the a region in the USA, right? I think I do one more for India as well, which perhaps is slightly easier to predict since like this seems to be watermarks as well. So like that's the output of the model right there. In terms of the crop classification, right? So like we repeat the same process. So like there is a pre-trained model from the Hugging Face repo by IBM and NASA that's called 100M multi-temporal crop, right? So like in this data set, you do have temporal information, right? So like we have 3 timestamps that are being expected for the input of the model, right? This image that I'm loading for the example, which should also be on your software path there, right? You're going to see that it has 3 images, each one of them with 6 layers, and that's why they are concatenated image-wise, right? So like that's why you have a 16 there. This model is expecting an input image that's back to 224 by 224. These specifications you can check directly in the config path of the model, right? And for this image, right, that's the type of outputs that would get, right? Which like each one of these different colors here represent either a type of crop or even water, right? So for example, this is very clearly some water-related feature there, right? So this was classified as being open water. I think that's the only thing that I can visually verify. Everything else in terms of crop, I cannot, right? But once again, like that's the analysis that would like you guys to do for your own data so we can validate the performance of this method, okay? For the proposed exercise, besides the download of these images for your region of preference, right? I would like you guys to also be able to run these pre-trained models exactly the same way how we did, right? For this very brief tutorial here on these other 3 images, right? That are from the same region, as you can very clearly observe, but different time points. So like, I don't know if you guys can see there, right? But there are small difference in terms of the features, which I cannot visually say what they are, but like this looks darker in here in particular, right? So like, I would like you guys to play at least with like the flooding detection and the crop segmentation algorithm, right? And hopefully be able to do the same for like your downloaded image, which Pepe has a script, and I think you already shared on Discord, right? That you can use that script to download the image for some coordinates of preference for you. Questions? I think it's very hard to have a question when you're not executing the code yourself, right? So like, yeah. But in any case, I think now that you guys have at least this, right? And you can use this Jupyter notebook that's already in the Spatial Ecology website as a reference on how to run this, we can address how we can get this code to work for you on your own computers, okay? Okay, how am I doing with time? 2:40. Should we go to your thing? Okay, yeah. You know, yeah, let's do that. Let's do his big data story, okay? And then the remaining of the day after the big data story, we fix your bugs, okay? Sounds like a compromise? All right, guys, okay. Yeah, sorry about that. Okay.
So I think now everybody is a bit overwhelmed with the things. I don't know if we should do the big data story now, or maybe postpone it for later or even for tomorrow. So what do you feel? Yeah. Yes, yeah. So we can easily do the tomorrow 2 big data stories and just continue now working on this. But maybe I would suggest a break, yeah, or like 5 minutes or something like that. I mean, I don't need it. I didn't follow the tutorial, but maybe you need it, yeah.
Yeah.
Yeah. So just jump back, take some coffee or refreshment, and yeah.
Okay, a bit more information, okay? So, so few ways how you can get this thing to work, right? Apparently, if you copy the ML folder to your home directory, right, and run everything from there, then everything works just fine. So, you guys did that already? Excellent. Okay, who here didn't get the thing to run yet? Okay. Oh, great. That's better than I expected. Excellent. Okay. So great. So now the proposed exercise, right? So now just 1 second. So what I want you to at least be able to do by when you leave, right, is to go to the proposed exercise in the Jupyter notebook that's in the Spatial Ecology website right now. Do we have Discord here? No, we don't have Discord here. Excellent. So Pepe, can you post the link again just so everyone has that like very easy to access? In the lower part of the notebook, you're going to see proposed exercise. Maybe you can share your screen there, Pepe? Okay, great. So I point from here. Great, yeah. So like if you scroll to the lower part, you're going to see proposed exercise. Oh, I think it's higher. Higher. Just do Ctrl F proposed exercise. Yeah, right there. Yeah. So what I want you to do it's at least to download this image, okay, that you're seeing here. This image, they might be already like in your path. You see that I'm loading that like from local in temporal. So like that, those images should be available for you. If they're not, I can show you where you can download them from, okay? And then I want you to repeat at least the float detection and the crop classification tests that we did for this one of these three images or the three of them together. So like it's up to you, okay? And then there is the bonus exercise, which Pepe is going to introduce to you guys now.
Okay, in Discord, you can find two links. This specific link to download some specific yes. If you click over here in this link in Discord, you can arrive directly to the HLS site that is allow you to download harmonized Sentinel and Landsat data. Okay, so the downloading procedure is working with this software in particular that is already under software directory in our in Surf. There is something particular that you have to take care is you have to create an account, okay, and save it your referential as a username and password inside this file that is going to be set directly under your home, okay? So you need to create a file with inside this specific. Then you need also to create a file, another file that is called tiled file txt with the tiles that you are interested, okay? And in particular, you can see the specific of your location directly under here. Okay, so over here you can see one particular area, and in particular if you click over here you have also the vector file of this one, so you can really download, I mean pick it up. This way, okay, you can zoom in and see the yeah, you can even get from here as a little, I mean, I can see my screen. Okay. Okay, so you need this number to load it inside, I mean, to load it to write inside to this little text file. Okay. Inside to this little text file, and then you can define your date of range that you want to download. Don't put 2 years because if not you download everything. So just 1 month is more than enough. Okay, and then you can run the full scripting procedure that I have been reported here, and we can look together. So you second. This one, can you see? Okay, you can check in Discord where I am if you don't see in the screen. So you create a directory, HLS, then you point where is sitting the file, the scripting procedure, and this one you can run. Then this is the little file with the name of the tiles from to, and the HLS folder that is pointing where all your Sentinel and Landsat image will be located. Okay, it should be straightforward now, especially with already knowledge in Bash. At that point, after running, exit, you should be able to see under your HLS a folder structure that has the L stay for Landsat and the S stay for Sentinel, where you have the image that you just downloaded, okay? And you can use some of them to, because you are going to download a few of them, I mean quite a lot, and you can select one to apply the same technique, okay? Be sure that the Antonio algorithm is going to use just few bands. So be sure that when you, if we say, for example, *.tif, maybe here there are more. So pay attention about this. So if your scripting procedure has been already run, the one that Antonio presented, you can shift with the new data set.
In fact, when you load the configuration file, it specifies what's the number of the bands. So I can paste there in case that you're gonna download the full thing with all the 12 bands. I can let you know which one are the bands that you need. I'm gonna send that on Discord.
Also, before to run it, be sure that you open few images that do not have cloud. This is not a mosaic. They are raw image. So you can get one with cloud, okay?